be doing is a lot of Python, which I'm sure you know because you signed up to this. I will briefly introduce kind of the format and what we'll be doing and what Python is and isn't, and then we'll go through and start working on our worksheets. So Python, of course, is a programming language. You can run it locally on your computer, but it also has options to run in slightly different places. So what we'll be doing today and for actually the next four days is running it in a browser, which is not the way that I would typically run it for my hardcore analyses, but is something that people are increasingly doing for example, publishing code alongside papers, but also is very convenient for teaching. So one thing that we can do now is be on exactly the same page. We can run our code from our browsers, and it means that you don't have to go through the bother of installing everything and dealing with the idiosyncrasies of your local operating system. We switched to this. Well, I definitely switched to this quite a few years ago, even pre-pandemic, because it just was such a nicer way of doing things than having to run around everyone in a workshop for the first like 30 minutes that it ran, just to deal with all of the Mac OS specific problems mostly. So it's a really nice tool, and we'll dive into it in a second. But I just wanted to preface with saying that you can run things locally as well. And in fact, at part of the day, we'll talk about how to install Python locally and what you want to look for. So if you are hoping to do that, also totally fine. If you aren't, just following along with the worksheets is actually all that you need to do. And it's really all that you need, really. So that's for the next 4 days. And we'll have moments where we can talk about how to install things locally. We'll do that later today. And then also there'll be opportunities to ask about your personal plans and specific questions on day number 4, where I leave a bit of space for dealing with individual questions and just more open questions about Python in general, even if you might not currently face them. Just like, is package X available, for example, those kind of questions. Or I want to map out on a world where emissions are, or I want to do linear regression with 300,000 variables. How do I do that? Those kind of questions are for day number 4. Lovely. So what we'll do today, as I said, is go through all of these, go through at least one worksheets. Lovely. All right. So Python, it's a programming language. It's a very big programming language in the sense that it's very, very used. It's a very popular programming language, is what I'm trying to say. It is a really useful language in the sense that it's general purpose. So it can do many, many things, from hosting websites to doing very basic software communication, to talking to hardware of very specific subtypes. For example, in my lab, I use it to talk to my eye trackers, my webcams, my EEG equipment, my other physiology equipment, and a whole host of other weird and wacky things. I've used it in the past to stream a live stream of a hamster to the internet, which isn't super interesting because they don't do a lot, especially not during the day, but it was a fun little code project. So it allows you to do many, many things, as I'm trying to say, including a lot of the stuff that we need to do for research. So data loading, data writing, visualization, and statistics. And that's the majority of what we'll explore. Before we dive into that, though, we'll talk about the basics of basically every type of programming language, but obviously specified in Python. So some of these concepts you might already be familiar with if you have some other experience with other languages, and particularly the more what I call high-level languages. So Python is, the philosophy behind it is to write code that is legible. So a lot of the code is sometimes said to be closer to English than to computer code, which might or might not always be true, but it's kind of the philosophy behind this, right? Something should be easy to understand if it's written in Python, maybe more so than if it's written in like a lower level languages like C, C++. They're a kind of fundamental building blocks of each programming language, and that's what we're going to talk about today. So there'll be a few pieces of jargon that I just wanted to start off with. And again, you might already be familiar with them from dealing with other pieces of software, but just so that everyone's on the same field, we're going to go through them anyway. we'll have certain values, and those values can be any kind of different thing that's known to a computer. So it can be a number, either a whole number or a fraction. It can be text as well, and in fact, you'll come to see that it can contain arbitrary objects as well. So the values are the kinds of things that we're going to talk about as the real things. Variables are essentially addresses. So they form a link to those values. So for example, you can have 3 as the value, and your reference to that can be A. So A would be a variable, 3 would be the actual value. And you could potentially see that as an address, right? The house is the real thing, but the way we refer to the house is by its address name. So, whatever number on whatever street and a postcode, those things are the direct linkages to the house. We can change the postcode system, which we might change variable names, but the underlying value is still going to be the house. There might also be 2 different names, right? So I live in the UK where we have these very old houses. They're sometimes just known as the name of the house, but they've also been given an address. So there might be 2 variable names that lead to the same underlying value, i.e. 2 different addresses leading to the same house. Lovely. Statements are things that we'll see very shortly. They're called if statements, while loops, for loops, those kind of things. They're essentially parts of the code that allow you to either go down a forking path, do one thing in one condition, another thing in another condition, or repeat the same block of code for a bunch of times. We have functions. And functions are basically little blocks of code that we give a certain name and that we can then use to run later as well. So sum is an example that I give here, where through a few operations that you define in your function, you basically allow the computer to do the summing of values. And by putting that all into a nice function, you can refer to it very easily on and on and onward. And then finally, and this is the most complicated one, we have classes. And this is a very specific thing about object-oriented languages. We'll talk about it a little bit later. It is something that is essentially a collection of variables and functions sometimes. So you can think about the class as a blueprint. For example, for a car, it has a few definitions in there for how the car can drive, how you can start it, but also it has variables in there for the number of wheels or the size or the number of doors, those kind of things. So a class is essentially a collection of functionality and specific variables. The tricky thing is that as part of a class, we call the variables parameters and we call the functions methods. So if you hear those names later on, hopefully it'll ring a little bell, and you might notice that we're dealing with classes. A lot of this is kind of implicit in the language because in Python, technically, most things are classes. I'm going to kind of skip over that because it's a really nice fact to throw out at a certain type of party, but it's not super useful otherwise to know. So what I'll do is I'll explain all of the syntax and how to use it, but it won't necessarily explain too much about the architecture in terms of classes underneath that, which I think is the nicer way of dealing with this kind of information. Right. All right. So without further ado, let's get started. Python has those variable types I just explained, and what we'll do now is just go through the variable types and see how we can use them in written Python. So all of these blocks you see here, they are a nice part about these notebooks, and they're essentially for running code. So what we can do here is hover over and see a little button crop up. It's a little play button. So if I click it, it starts loading Python in the background, which can take a little while. And actually, if you are, hey, there we go. There we are. I promise that it only takes a while on the first one. Now that we're connected to a backend, we can click much faster. But the idea is essentially that these notebooks are really nice because they have words in them that I wrote to you. So human readable words, as well as code blocks. And the code blocks are what we just activated. Don't feel like you should read everything in between. What I essentially do is talk through all of these things. So you don't really have to pay attention to the writing, just pay attention to the code blocks. And the idea is essentially that the writing is there for your future reference, right? It's also provided as a PDF. As I said, you'll have access and retain access to these notebooks as well. So you can just, or you can even download them and use them for yourself, then you'll have access indefinitely. So basically, treat these as information for later. So if you want to look something up, treat them as a reference, or obviously if you follow this asynchronously, do feel like you can pause me and read through as well. Cool. So we just did this addition. So 1 + 1 results in 2. We can say 5 - 3 as well. We have another positive number. We can go -2, and we can multiply, and we can divide. So all of the things that you would stuff into a calculator also include into most programming languages. And this is a nice way of doing that. Sometimes if you feel like you need to do a few sums, just put up Python and punch that in if you feel like it's easier than putting up a calculator. But obviously, more complex things will follow on this. For example, assigning things to a variable. So what we're doing here is saying a equals 3. And equals here, I'm going to call this equals once and then never again, because the equal sign doesn't really mean equals. What it means is I assign 2. So what we're doing is we're assigning 3 to a being the variable name and 3 being the value. So this is that kind of address thing that I talked about before. The address a now points to 3, and we can later overwrite those things or add different references, addresses, essentially. The crucial thing here is that this is not necessarily an equation of two things. I'm stressing that now because we'll come to the actual equal sign or the equals operator later. And I wouldn't say a lot of the errors that I still make in my coding is whacking a single equals in when I mean the actual equals instead of the becomes. Anyways, what we're saying here is that 3 is now pointed to a, and therefore we can do the same operations to a as we could do to 3. So essentially a becomes a stand-in for the underlying value. So a now, the variable we can work with and we can change if we wanted to as well. We'll come to dealing with variables a bit later. So those are integers, whole numbers, we call them integers. Next, let's turn to floats. So floats are representations of fractions. And there is a sort of an important, but also probably not super important for most purposes, kind of side note to this. Computers can represent the exact decimal, but have a clever way of representing numbers instead. It is kind of like a fraction between two integers, because integers we can represent in computers. And we have a large precision on those integers. So again, this is kind of a technical note that might or might not be of importance. So it essentially means that 0.1 isn't always represented exactly as 0.1, but rather as a fraction that is very close to 0.1. Which is also why you call floating point numbers, because that refers to the representation. Anyway, for most of our purposes, they'll be fractions. So 0.5 plus 0.6, 0.1 would be 0.6. We can do addition with them. We can do subtraction with them. We can multiply them, and we can also do division with them. And as before, we can assign them to variables. So a is now becoming 0.5, b becomes 3, and then we can multiply a and b together to form 1.5. Lovely. So those are the basic operations. There's a few additions to that. For example, exponentiation is the double asterisk sign. Can be a square, can be anything else as well. And then I did want to make a small point about division, because there are certain expectations you might have of division. I think Python, in its current iteration anyway, Python 3, which is what we'll be using. So there's different Python versions. I should probably say the current version is Python 3. That's probably the only version you'll see. There was a change over time not too long ago, but I think most things that you'll use in practice have been changed over from Python 2, which is a previous version that kind of existed in parallel alongside Python 3 for a long time. This is currently more or less a historical note. It used to actually in practice be a problem where some libraries were only compatible with 2, but no longer, but not with 3. I don't think that's the case anymore. So let's skip over that. Regardless, In division, what Python currently does, I think, is the intuitive thing. So if I say 5 divided by 2, I get 2.5, which I think for most practical purposes is the easiest thing. However, you could be a stickler for the rules and say, well, a division is an integer division. If I divide the whole number 5 by the whole number 2, actually what I have is 2 with a remainder of 1. So my answer could be 2. And if you want that, if you want an integer division, you use the double slash operator. So that gives you the actual integer division results without the remainder. And if you wanted to get the remainder as well, you can also use the percentage operator. So 5%2 actually means I want the remainder after dividing 5 by 2. So that's 1. So, the classical kind of math test that you would do. Lucy has 5 apples and wants to divide them between 2 people. Everyone gets 2 apples and Lucy has a single apple left over. That's this kind of thing. Again, Python currently does this automatically. There are situations in which actually the default division is an integer division, so you get this kind of behavior instead. We'll talk specifically about that when it happens. In general, you don't necessarily need to be too aware of the difference between integers and floats in this case. So I'm going to skip over this because, again, it's kind of an historical note now. With one exception, but we'll talk about it when it happens. Cool. So those are numbers. The next thing up is text, which we call strings in programming, and they're quite flexible. So in Python, they are text that is bookended by double quotes. So we can run this. It's a string. It can also be bookended by single quotes. We can run this. It's a string. The benefit of that, I suppose, is that you can use single quotes within the double quote bookended string without messing things up. You can also use double quotes within the single quote bookended string, which can also be nice. And alternatively, if you wanted to use either of them, you can bookend either with 3 double quotes or 3 single quotes. Both of those things are what we call doc strings. Don't currently have to know why that's the case. We'll talk about that in a second. But it allows you to use any kind of single or double quote within your text as well, within the content of your string. You'll see them crop up as / apostrophes. That is because that's the way that Python internally represents them. Cool. Why are there so many ways to define a string? I don't know. Historically grown that way. I typically stick with only one of these representations in my code because it looks slightly nicer, but you're very welcome to do whatever you want. That's kind of a matter of preference rather than anything else. As I said, if you want to represent a single quotation in there that's like an apostrophe, then you probably want to go for the double bookends, but you can also just use 3 of them on either side. Again, this is up to your personal preference. Lovely. So these are all strings with actual text in. They can also be empty, which is maybe a silly note. Maybe it sounds super unimportant, but empty strings are evaluated as an actual empty thing, a bit like the number 0 for the lack of any value. And it's therefore maybe important to note that it can be. And also, you can use some mathematical operators on strings as well. So you can add them, which is basically just placing them together using the plus operator, which can be a nifty trick. You can also multiply them, and then you get a number of them. So if I say 3 times a certain string, I get 3 times that string back, which, these make sense. Obviously, things that are less sensible, like division or subtraction, they don't really work. So it's really just these 2 operators. It's not necessarily the whole set of mathematical functions. Lovely. Speaking of functions, one thing that we'll do a lot is use the print function. And this is something where, so a function is something that takes an input, produces an output, or does something else with the data. It doesn't always require an input. It doesn't always produce an output. We'll talk about that a little later. I just want to bring up the print function here because I'll be using it a lot in these worksheets, specifically mostly for strings. And the idea is essentially that one thing we can do is assign things to variables, like this over here. And then what we can do, either with those variables or with strings, or actually with any kind of data value, is we can print them. Print really doesn't do anything but show it to you. And the reason that that's potentially useful is that what we've done before all produced an output, right? So you could see the end results. And that's purely because it was the last and only thing that we did within this code block. However, if you assign things to a variable, for example, or if you have many different parts of a code block, depending on what kind of environment you run in specifically these Jupyter notebooks, only the last thing crops up. And what we want is maybe have a little bit more information throughout the process. So for example, if I define a string variable, if I assign this string to this variable, I don't get any outputs. And if I wanted to see what the actual content was, I can always use print, and that gets me what I want underneath the code block. So it's a nice way of just interrogating what happens during a process that we're coding. We'll see this quite a lot during the rest of the worksheets. For example, to get our statistical values like t-values and p-values out, or to see what the content is of a certain variable if we load data, for example, from a file. So the idea is that print is a useful thing that we'll see a lot during this, and it works because it's a function that takes an input, and the output, the result is that it crops up underneath the code block. So one thing that's nice to kind of show its function is string formatting. So we're doing here is we're defining a string, and you'll find a bunch of curly brackets. So I have here a bunch of curly brackets before. Interesting is that we can actually start using those curly brackets to fill out arbitrary values. So for example, I can say my string variable name is s, a full stop, just change that, a full, and then the format function. So this is neat. This is also just demonstrating that some variable types come with built-in functions that you can use. These are the methods I talked about earlier. The string is actually a class. But the idea is essentially that what this function does is it puts in those placeholders values that you define. So in this case, I'm going to insert into my string the value 42 and the value the UK. So if I run this, I get the formatted string for I'm 42 years old and I live in the UK. I can also do that with other strings and also with floats. It doesn't really matter what the value type is, as long as it fits within a string, it'll work. So there we go. There's the original string, and then there's a string formatted with different types of inputs. So 42 UK, 20 the sewer, those kind of things. This is a neat little trick. There are a few more a few more functions built into the string that you can then pass variables to. The idea is essentially that we can use these later in the sheets to kind of interrogate again what we did with certain bits. So it's a useful tool that I have introduced now. It'll hopefully stick around in the dark corners of your brain, and it'll hopefully crop back up when we see them next. But that's printing and string formatting. Any questions so far? Lovely. We're moving on to Booleans. So Booleans are a very specific type of variable, data type rather, and name perhaps, or it sounds like a technical name for actually what is the most simple type of variable you can probably imagine. It's something that can either be true or false. That's it. It's named after Edward Boole, mathematician, logician, and that's where the name is Boolean. And the idea is essentially that this is kind of a very low level thing in computing, right? Your individual components can either be 0 or 1. Great question. What I think you did probably, Malcolm, if you click print S and got a name error, did you run the previous block? Which leads me to my bit that I maybe should have introduced before. You can run these code blocks in any kind of order that you want to run them in, but they are written in such a way that there's dependencies. So you probably want to do them in order. So for example, if I'm right about the error that Malcolm just hit, it probably is that, yes, they skipped this block, which is a perfect example. So thank you for doing that. So they skipped this block, which means that the S variable wasn't actually defined. And then if you start referring to that variable, Python is in a panic because it doesn't recognize the variable. It just tells you, mate, I don't know what to tell you. I don't know what this variable is. So nice learning opportunity for two reasons. One, if we tell a computer to do certain things, it'll do exactly those things and it won't understand other things that are beyond it. And it'll give you an error message that is informative in most cases. Sometimes less informative than other times, but on the whole, hopefully a good indication of what went wrong. In this case, the name error basically tells you, hey, I don't know what this name is. I don't know what this variable name is. The other lesson is that within these worksheets, because we've introduced some serial dependency, you'll have to run them. And sometimes it's easy to skip one. And therefore, if you skip one and you get a name error like this, first thing to do is check, did I run everything prior to this? Or did I kind of mess about with the order? And then, run whatever the immediately preceding or wherever the variable is defined in the past, run and then see whether your output works for the later code blocks. Fantastic. Thanks very much for the opportunity to highlight that. Cool. Back to Booleans. So your lowest level thing in your computer can be on or off, 0 or 1, and true or false is kind of a similar reflection of that. So you can think of a Boolean as a number that can only be 0 or 1. And the computer actually kind of treats them like that. So it can define A as true and B as false, for example. And then, we have variables that are lying kind of 0 and 1. The way they can kind of visualize that is by trying to do mathematics with them. So there are proper Boolean operators, and there's also this. And this is essentially multiplying Booleans. So 3 times true or -1 times true, for example, actually gives you 3 and -1, which is very rarely what you want. And therefore, I'm just kind of not necessarily warning against this, but kind of using this as an example of, showing that true is actually just 1 and false is actually just 0. The proper operators to use aren't necessarily a multiplier, but they're really and, or, and not statements. So these are logical statements. You might be familiar with them if you spend a lot of time doing library searches or desperately trying to get papers out of Google Scholar, where and, true, and not are also terms that we use quite frequently in these kind of bibliographic terms. These work in much the same way. So an AND statement evaluates two Booleans, and if both of the Booleans are true, then the AND statement also returns true. If one of them is true, but the other one isn't, we return false, and if both of them are false, we also return false. So true and true would be true, true and false would be false, and false would also be false, which is indeed what you see. The OR operator is a slightly liberal cousin of this. We say true or true is true, true or false also is true, and false or false also is true. So if we basically combine this into true, or, and then 300 falses, we still get true out of this. So if any of these are true, then we get true. Whereas for AND, if all of them, we get true. So OR is slightly more restrictive. AND is slightly more restrictive when it does than OR. And if the not operator, which simply negates whatever it does. So not true would be false, and not false would be true, right? That's relatively straightforward. So basically we have all, any, and reverse. That's the other kind of way of thinking about and, or, and not. You can chain them as well. And I would recommend chaining them in such a way that you treat mathematics, so true or false, done here between brackets. So that's evaluated first, just like in any other mathematical statements. Within the brackets is what goes first, and you work kind of to the outside, to the larger bits. So this one is evaluated first. So true or false would be true. False and true is going to evaluate to false. And then the total here is true and false, which is also going to evaluate to false. But the crucial thing here is that these Boolean operations work much the same as mathematical operations, You can protect them as in make sure that they happen first by putting them between round brackets. Cool. The reason we have Booleans is that they're actually exceedingly useful, and they're really useful because we'll use them later in parts of code that can only stop after a certain condition is met, or we'll run one thing if one condition is met and another thing if another condition is met. Sorry, that was me accidentally tripping my desk chair and falling by like 10 centimeters. We can just define things as true or false, but maybe a slightly way of using them is by using comparisons. And this is what I was defined by a double equal sign. So 3 equals 5 is a logical statement, and it is not necessarily true, right? 3 equals 5 is probably going to evaluate to false. 10 equals 10, true, and A equals B is also false. So it's great. That works out nicely. You can do this with any kind of value comparison. So we've compared integers here and strings, but it can also be floats. It can also be any other class. Another thing that we can do is not just check if things are equal, but also if things are smaller than, greater than, smaller than or equal to, greater than or equal to, or do not equal. The smaller than and greater than are just borrowed from mathematics, right? It's the crocodile beaks, if you've learned it in that way. The smaller than or equal to is the smaller than sign and then an equal sign pasted together. And then the greater than or equal to is a greater than sign and an equal sign also kind of pasted together. So syntax-wise, this is what you want. And that it does not equal, slightly more weird perhaps, it's an exclamation mark followed by an equal sign. So that's the syntax. You might or might not have seen this before. Again, in other programming languages, sometimes it's defined as this as well, sometimes slightly different, but that's the not equal sign. So we can use them in ways like this. So 2 is smaller than 3, should return true. A does not equal B, should also be true. And here we have one that says 2 plus 3 is smaller than or equal to 8 minus 3. So this is 5 and this is 5 and it should be equal. But also 3 is smaller than 8. So depending on what it evaluates first, you're fine here. This is one of those tricky ones, actually. Let's run this first just to see that we're right. Yeah. This is one of those tricky ones where just by seeing this, I know which is that things are evaluated within these bits first, and then the evaluation is done. So you first get 5, and then we get another 5, and then we're equating them. But maybe it would have been safer to employ a few brackets here, just to make sure. Oh, that was me putting in the wrong bracket and then missing the backspace. There we go. So we put in brackets, then we would have been slightly surer of what would have happened. If you don't put in the brackets and you don't know exactly what the order of operation is, you might risk doing this evaluation first and then dealing with that in a sum afterwards. So yeah, just be careful when you do these things. Again, this one is safe. I know by heart that it is, but just to be sure, you can always sprinkle in some brackets. They won't have a downside. And then finally, you can kind of chain them as well. So this, much like other mathematical operations, says, is 10 smaller or equal than 20? And is 20 smaller or equal than 30? And I just return a simple true. If we have a value in here that's that doesn't meet those criteria, like false out. So it's a nice way of doing something that you might be familiar with from just mathematical notations, where you say A is smaller than a number that I want to check against, and that should be smaller than B. So is this within a certain range between A and B, essentially? Cool. Slight note on syntax. The AND operator can be written as the word AND. Again, Python, the philosophy is we want to stay relatively readable, so it's quite close to English, so we can just write AND or. And this works many of the times. You can also write them as an ampersand AND, or as a pipe, straight line up, for or. And these will become salient later when we start talking about NumPy, which is a library that allows you to do a lot of numerical operations and will we'll reintroduce these essentially when they come back. For now, they are interchangeable. For NumPy, they are not. But feel free to just write and or make your code more readable, I think, in general. But also feel free to use the ampersand or the pipe. You can use either, right? It's fine to be a bit on your personal taste in this one. Cool. Any questions so far on Booleans or comparisons? Lovely. Cool. So next bit up is collections, and collections are different types of values in Python that allow you to kind of combine other values. So it's a slightly confusing concept where the top level variable will be recognized as one of those collections, but inside of that collection, you can have integers, floats, other collections, literally any given value type you can have in Python can be stuffed in a collection, but the top level thing is then the collection. The first one we'll look at is called a tuple, and you recognize it by being bookended, or at least it's a series of values that's bookended by round brackets, and the values themselves are separated by commas. So 1, 2, 3, and around there is the round brackets. So this would be a tuple. So a tuple now contains all three values, 1, 2, and 3, and we can start looking at those values by using an index. And it's quite an important concept. So the notation for that is, I'm going to remove the print statement just for clarity. The notation for these indices is my variable name, and directly after a square bracket, and then the index number, and then another square bracket. And now you might be wondering, that index number is 0. There's two types of programming languages. One does zero-based indexing, and the other is wrong. So it's a little joke. There's 1 and 0-based indexing. Some people swear by 0-based indexing. Some people swear by 1-based indexing. Different programming languages do different things. If you want to inspire a flame war on the internet, go to any kind of programmer forum and argue strongly for either 0-based or 1-based indexing, and the other camp will respond to say that you're wrong, actually, and it'll become a riot, essentially. So if you like an entertaining evening and you are into studying flame wars on the internet, this would be a nice place to start. Would necessarily recommend it. There's a lot of kind of annoying arguments about this. Ultimately, it comes down to it kind of being a design choice. Many programming languages start at 0, but there's some larger ones that are quite useful as well that start at 1, and there's good arguments for both. I'm going to be very wussy about this and just kind of use the arguments for both sides. Anyway, 0-based indexing is what we do in Python, which means that we start counting at 0. So the first index is the 0th index, essentially. And I'll try for now to talk about 0th, 1th, 2th, just to kind of disassociate it from what you would actually say first, second, and third, which might already be an acknowledgement that this 0-based indexing is a bit different than what you would expect, and maybe not as intuitive as 1-based indexing. But anyway, the bottom line is that if I want to find one of those values within my collection, I can use the indexing method, and I use the variable name for that, a square bracket, the number of the index, and another square bracket. So if I put my print statement back in there, what I should get now is 1 for this one, 2 for this one, and 3 for this one. And that's indeed what you get. There's a nifty little thing here. Excuse me. There's a nifty little thing here, which is actually kind of a strength to, I guess, 0-based indexing. So if 0 is the first index, and I go to -1, I basically go round the back, right? So I should end up at the last index. And that's actually what you get. So if you just get the last index out with -1, you again get the final value. And you can do this until the first value. So if you say print a -2, it should be the penultimate value, and that's indeed what you get. There we go. So you can basically do this from the back all the way to the front. This might seem like a triviality now, but actually this can be really useful to do counting from the back, which is actually super useful in some cases. So nice thing to have in the back of your mind. And it kind of flows very nicely from the 0 at the start, right? So if my first value is 0, my final value -1 kind of makes sense. Right. One thing you might also want to do is alter the values in a collection. So if I say A index 0, I'm going to try and change that 1 into a 2 by saying A index 0 is now a 2 or becomes a 2. And that gives me an error. And specifically, it says the tuple object does not support item assignment. And that's because tuples are what we call immutable. And immutability can be a really nice feature. It basically means that once you define this tuple, the only way to change it is to completely overwrite it, which prevents kind of accidental changing of individual values in there, which can be really useful if you want to avoid changing something that should be constant. So for example, if you have a screen size for a specific experiment, and you want to always run it at that screen size, it's very likely that the participant that you're testing is always looking at the same display. So the resolution is probably not going to change during that. So having the resolution in a tuple makes a lot of sense to prevent accidental manipulation of that. And similarly, if you're using specific constants within an analysis script, you probably also want to maybe pop those into a tuple to prevent accidental alteration. But there are other scenarios where you have a collection of values and you do want to change them. For that, we can turn to the tuple into a list. So a list is essentially like a tuple, but it can be altered. You recognize it by looking almost the exact same as a tuple. So we still have values that are separated by each other by commas and also bookended, but now they're bookended by square brackets. So the tuple was bookended by round brackets. These ones are square brackets. The same is true for lists as is for tuples when it comes to indexing. So if we want the first position, we can say A index naught. For the second, A index 1. For the index 2. And that gives us the individual values. But also, we can alter things. So for example, what we can say is, actually, I want the 0th item in my list of A to be the same value, but then add 5 to it, please. So the first time that becomes a 6. Oh, sorry, I forgot to run the bit where we do item assignment. Whoops, that was still a tuple. There we go. So in the first iteration, it becomes a 6. And if we run this again, we again add the 5 to that position. So it should be 11 and so on. So this is really neat. We can start changing individual values now. So again, this operates much the same as a tuple. You can index the individual values in there, but you can also get changes made in that same list. The one thing you can do is change the whole list. So in this case, it's a list of all numbers, but it doesn't have to be, right? It can also be a list of some numbers, some strings, some other things altogether. So operating like a list of numbers isn't entirely possible, which means that if I just say A plus 5, I get an error because it's just not supported, right? We'll come to doing what is essentially a vectorized operation later when we start talking about NumPy. So this would be vectorized in the sense that I want the +5 to operate on my entire list of values A, which is something that is possible, but again, we need a slightly different library for that. So we'll turn to that later. For now, individual item manipulation possible. Via this syntax, impossible. So if I define my list as 542, for example, and I say a.append 1, I get the list with the 1 added in there. So this is neat. It now says 5, 4, 2, 1. This list is going to be permanently altered by my saying append. Append always adds an item at the very end of the list. What I can also do is insert values at a specific point. So for example, what I do here is say a.insert. So same syntax, right? I use my variable name, a full stop, and then the function name. What I'm doing here is for the second index, or index 2, third index, I'm adding the value 3. So if I do that, I should now get 5, 4, 3, 2, 1, and that's indeed what I get. And then finally, we can look at the index as well. So if a value is in a list, the index number will give us back the index at which that value occurs. So for example, a full stop index of 4 should give us the index of 1, because that's where the 4 is within this list. And that's indeed what we get. Cool. Indexing, quite an important topic in programming in general, and also obviously therefore in Python. So if you have any questions about this, great point to ask. Right. Cool. Seems we're all on board still, which is a good sign. The next and final collection we'll talk about now is the dictionary. And a dictionary kind of functions in programming like a dictionary functions in real life. So, for example, to kind of stress that point, I here have a dictionary where I define a few words. So Python, for example, and I have a colon behind that, talking about like, how do we talk about these things? A dictionary is bookended by curly brackets, and then in between we get a specific type of value. The value that is before a colon is called a key, and then the value after a colon is called the value. So in this case, essentially what I have here is a variable name, Oxford English, a dictionary recognized by the curly brackets, and a very long value assigned single key. So now if I say Oxford English square bracket notation, because we're indexing in a way, but now we're not indexing by number for a specific position. What instead we're doing is indexing by the key. So that's what we're doing here. And you get indeed back what I put in as the value assigned to that key. So that's an example with one thing. It's not super important. What we can do as well is define a dictionary that we then assign individual keys into. So here we define a dictionary with the values in there already. And you can already see this can get quite long. Another thing that we can do is define a dictionary as an empty dictionary first, and then start defining the keys one by one. So here, essentially what we say is, I want a key that's called 1, just a string 1, and I'm going to assign that the value, 1. Same here, the key 2, assign the value 2, the key 3, assign the value 3, and so on. And now the dictionary is similar to what we saw before. So it's bookended by curly brackets. There's commas in between the different entries, and each of the entries is, in this case, a string, a colon, so that's the key, and a colon, and then behind the colon is the value assigned to that one key. So this is not unlike a list in the sense that this is kind of a list of 1, 2, and 3, but instead of having our index values to point at the different values, we have named indices almost, so keys as we call them here. Those keys can be anything. So here we have used strings, which is one of the more common things you see, but you can also use integer values, and that works just as well. And you can actually use any other type of value as well. Just that most of the time, that's probably not what you want. Although in some cases, Markov chains, for example, you might want to put a tuple in there for 2 items that point to a third item as its value. Is that clear? I just spotted that I forgot to take this out, but it's also a nice opportunity. So as someone might have noticed and did notice in one of the previous sessions, this is a variable name with an underscore in there. And there are different types of ways of writing variable names. Snake case with underscores is one of them. Camel case, where you provide a capital letter between each of the words in your variable name, is also a way of doing it. And there's also this one, it's camel case, but then the start is also a letter that is in caps. So all of these are totally appropriate. You can mix and match whatever you want. You can give variable names in general, like however you like them, as long as they're words and don't start and numbers. As long as the first one isn't a number, you're fine. What I will say is try to be consistent with what you do. So I try and always use snake case, even though I don't always meet my own rules. But yeah, this is convention, right? So many things in programming are convention and not necessarily checked by any of the processors that take your code and feed it into the machine. So essentially, you're free to do whatever you want. But conventions are suggestions that you do things in a sensible way. And the sensible way in this case would be consistent, which is why the underscore is totally fine within a variable name. Cool. So final thing to note all dictionaries is that if you have a dictionary, you can quickly get all of the keys out by using the keys function. So in this case, we say the dictionary name, that was D, the full stop, and the name of the function, keys, and that gives us a list of all of the keys that we have. So 1, 2, and 3 in this case, 2 being a string. Can be useful if you want to like loop over the entries into a dictionary, for example. It kind of depends. So sometimes you use these purely as a lookup. Sometimes you use these to potentially just as a named collection and a collection that is ordered. It's the other probably good thing to note that dictionaries don't necessarily have a strong order. Depending again on what kind of platform you're on, they might be ordered by history. So which one was the first one to go in there? But in general, I'd recommend against assuming that there is an order in there. If statements are part of the core building blocks of programming. So you'll see these in any given language that you use. And they're essentially a way of using logic. So the logical statements that we've seen before, like a smaller than 3, to go down one path in your code, or down another path, or down a third path, or as many paths as you would like. The example I'm going to use here for the start is a remainder, so whether a number is even or odd. So for example, we have here is the variable name A, is 3 is assigned to it. And then we compute the remainder as another variable, and that's A, the percentage operator 2. So this can be 0 if we have an even number, or 1 if we have an odd number. So if we then say remainder equals 0, so that's a double equal sign, right? We're doing a comparison of equality. Then what I should get, again, is a 0 in case that the original number was even. And now, what we can do here is use that in an if statement. Right. I am very annoyed about this internet. Right, guys, this is not the usual. Okay, I was saying if statements, core building block, many programming languages, all programming languages, in fact. And what we're about to do here is use this to our advantage, or at least use a logical statement in an if statement to kind of go down one of several paths. And what I just set out is this trick that we learned in a prior sheet of using the remainder operator to check if something is divisible by 2. If it is divisible, by 2, then we get a 0, i.e. the number was odd. If not, we get a 1. So we compute a remainder, and it's either equal to 0 for even numbers or 1 for odd numbers. Then let's jump to the if statement. So a bit of syntax here. We define our variable A. We assign 4 to it. And then what we do next is we do this logical statement. So what we're doing first is taking the remainder of A, and then we're comparing it to the value 0. So this logical statement is a core part of the if statement in general. The other core parts are that it starts with if, and then it has a end. So it's if logical statement, and logical statement, again, is something that evaluates either true or false, and then it ends on a colon. And then really crucially, the next bit of code starts at an indentation. So there's a bit of white space before that code. And in this case, it's 4 spaces. So 1, 2, 3, 4 spaces. It can also be a tab, and it can also be 4 spaces. It is 1 indentation. For now, let's assume that 4 spaces is the way to go, because it's kind of what is in the general recommendations. It's one of those agreements that we all have in programming. There are very good reasons for not using 4 spaces, but a tab instead for readability purposes for people who use screen readers. But the documents in kind of Python's style guides essentially say 4 spaces is how you want to go. So when I'm introducing you to the language, I also introduce you to that same concept of 4 spaces. Just know that it's not a universal given, and that it will also work if you hit a tab. The point of these statements is that if the logical statement within them evaluates to true, the code that is indented will actually run. But if this evaluates to false, this code is ignored. So if we run this, we should get this value is even. Whereas if we make this an odd number, we shouldn't get anything at all, because the code isn't ever run. So it's a really neat way of allowing your code to do one thing in one scenario and another thing in another scenario. We don't just have a single if statement. We can add different branches to that. So for example, in this case, we can say we add another statement. The other statement is elif, following the if statements. It's short for else if. So basically, this is only run if the first if statement doesn't evaluate to true. If this does evaluate to true, and this also evaluates to true, it's still not run. So you kind of have to work things in that are mutually exclusive, essentially, or at least partially exclusive, because you can also use this in a clever way to your advantage. But let's assume they should be mutually exclusive for now. So we start with the same thing, right? So this is the same if statement, the same logical condition, and the same colon at the end. Then we have the same white space, so the same 4 spaces, indentation rather, and the same code run if this evaluates to true. Then we have our else if, that's a new bit. So this is the opposite of what we said before. Is the remainder 1 instead of 0? It's the opposite because the remainder of 2 can only be 0 of 1. And then again, we have a colon at the end. We again have indentation, and we again have code after the indentation. So it's essentially the same as a regular if statement. It just starts with L. Right, so you start on here, compared to compared to the remainder of 2, and it's 0. So this doesn't ever run. But what it does do is jump to the next elif statement, and then it runs this code instead, because this else if does evaluate to true.